Hi, welcome to the day 3 of 100 days machine learning crash course. And in this session I'm going to give you some Python examples related to the previous sessions, and also we are going to complete our discussion about probabilities. Okay, at first I want to show you a Python code for curve fitting. If you remembered in the last session, in actually the first day, we talked about the problem of having some points, and the problem was that we are having a model with the parameters w, and this is w null plus w1 x plus w2 to wm x power n, and I told you this is a linear function of w's, okay? And our cost function was the mean square error, or MSE, which was sum over all data y hat minus y squared, and we wanted to minimize this regarding to w's. In other words, we want to find w which minimize the cost function. And the good news is that for minimizing this solution, for minimizing this cost function, we have an analytical solution. And so I coded that in Python, and I want to show you as a practical example in Python. And so let's say we have, this is actually the example of the first session. We randomly produce some x, and this is the actual function, this is the actual y that we want to estimate, and the estimator is y hat, and the input of the model is a feature vector of 1, which is the coefficient of w0, and then x, x2 to xm. So we could write the y hat as w transpose times x, okay? Actually, and this is a vector, okay? So now I just wrote that in Python to show you this example. In here, this is the main part of the code. The m is actually the degree of polynomial that we want to feed to the data points, so it could be 10 or anything. The n is the total number of our samples from the function of this sign 2p times x, and it could be, I don't know, anything, it could be 50. Then this is our data. We initialize them with ones, and actually we put all of the all of the sample points in a matrix. So for each sample we have x1, we have x2, and we concatenate all of these together and put them in a matrix and call it X. Okay, so we have X, and in this line we produce the random X. We want to generate the random sample, so we generate some random points from 0 to 1, and we have n sample points. Then we produce the features. The features are, for each sample, the features are 1, x power 1, power 2, and to power m. So in here we have a loop through 1 to m plus 1, because when the degree of polynomial is 1, for example, you have two features. You have two features, and your feature vector has two elements. Okay, so we fill that matrix, and then we calculate y, which is the sine of 2 times p times our random points plus a random noise. If you remember that our example was sinus sine of 2p times x plus a random noise. This is epsilon, and the epsilon comes from a Gaussian distribution with 0 mean and variance of sigma 2. And this is the mean of our Gaussian distribution, and the scale is actually the standard deviation, which is the square root of sigma 2. So the sigma is the standard deviation and the scale. So, and in here, if you remember that we add another term in the cost function to prevent overfitting. In here, which was the norm of the weights. In other words, we can expand it as a sum over all w's squared. So and add this term with a lambda coefficient. So in here we have some lambdas. We created a loop, and then in these three lines, actually we calculate the solution for this minimization, because I told you this minimization has a unique solution, and the solution is, as you could see here, it is it has two parts. We should first, actually it is, let me write that. The solution for this is, let me show it with W star. It is equal to, okay, this equal to x transpose x plus lambda minus 1 times is transpose y. So this is the optimal solution for this. So we could for each x and the lambdas and y, we could derive the best solution with this cost function. So if we do that and derive the w's and plug them into this equation, we derive some coefficients for our model. So we could plot the model prediction. In here for different x, we calculate the output of the model. Okay, so and plot that. Okay, let's run this code. As you could see, these are the sample data points, and this is the curve that we feed to these data points. And in here we actually we are increasing the coefficient of regularization, or in other words, we are increasing the lambdas. So as you could see, the prediction of model is more smooth and has lower variance, in other words, has lower changes in the prediction. And now let me to reduce the degree to 2. So the second order approximation is very like to a linear thing, if you see that. Okay, it's something like this. And so this is the first code. If you want, I could share it to you, or if you have any question, I could answer it to you, or ask it on Friday in the Slack, in our Slack session, and then we could talk about it in there. And it is pretty straightforward to write this code. As a second example, in here we just produced some random data points, and just want to see the distribution, the density function of the random variables. One of the very famous distribution is Gaussian distribution. In here it has 0 mean and standard deviation 2. We talk about it in this session, but for now just suppose that it is some kind of distribution with some parameters, and we sampled from this, we got n sampled from this distribution, and then plot the random data points. If we plot that, we could see that it is something like this. As you could see, the mean is 0, because in here the mean parameter of our Gaussian distribution is 0, so it is around 0. It has some fluctuations things, which is related to the scale. If we increase the scale or decrease the scale, the fluctuations changes. Let me put that to 0.2. Okay, as you could see, the scale reduced in here, so we have a the fluctuations are decreased in this signal. Now maybe we want to see the distribution. In other words, we talked about the density functions. If you remember that the density function was for each random variable, for the continuous one we had some density function, and now now we have some samples from a distribution and we want to estimate the density function. How could we do that? If we look at this as a frequentist interpretation of probability, one way is to actually quantize this axis into some beans and then calculate the probability with classical definition, which is the number of events occurred in this actual interval. Let me show it with n of I divided by the total number of our events. Okay, and then we could and we call them beans. Okay, so in here we just calculate the histogram of the data. So actually we call this procedure calculating the histogram, which is an approximation of density function. If I run that, you could see that the histogram is something like this. It is very similar to the actual distribution, which is something like this, the actual distribution of the Gaussian, and you could see that this is a very good approximation of that. If we increase our data points, it will be much more better approximation from this density distribution or density function. And as a last example, if you remember that we talked about the covariance of two random variables, and if we have two random variables and they have some kind of relationship, linear relationship between them, they have some covariance. And as you could see, we could generate some random variables which are dependent with covariance matrix, and actually with NumPy package you could create some data and plot them. If we plot them, this is important. If you want to have independent variables, you could put the matrix of covariance on the diagonal something, and any other position other than diagonal equal to 0. If we put something like this, put it 0 and 0, and no, this is another code, sorry, Python 3 random 2b. As you could see, it is some kind of circular, means that x and y are some kind of independent, and they call actually isotropic in this case. But if we put some values in here, and it is better to this value and this value be the same. Actually they should be the same in the real valued case, and some nice conditions which we have in the most common cases. So it is 20 and 20, and then if we run that, we could see that it is some kind of it shows some kind of linear relation between x and y, because this is some kind of line that relate x and y distribution together. So in this case, x and y random variables are dependent with a linear relationship together. Okay, let's move on and continue our probability discussion in here. Okay. Now we want to talk about the Bayesian probability interpretation. Probability. If you remember, in the previous session, we talked about the frequentist probability interpretation, and we got this definition that in the classical probability definition, the probability of x is equal to, let me write it in more clean way, xi is equal to the number of events divided by the total number of trials when the number of trials is very large or infinity. The problem with this case is that sometimes we cannot do an experiment infinite times, or in other words, it doesn't make sense to do so. Consider that we want to know that a black hole exists or not. This is an uncertain event for us. Or we want to know that whether Arctic ice cap will be disappeared in the next century or not. Okay, this is not an event that can happen repeatedly, and we could calculate the probability by running this experiment 1,000 or 1,000,000 times. Okay, but we could state something about these events. For example, if we have the satellite pictures, satellite images from the planet, and we could say that, okay, the temperature of Earth is increasing, so because of global warming, for example, so it is likely that in the next 100 years the Arctic ice cap will disappear or something. So we could have some kind of belief or degree of uncertainty to this. This is actually the Bayesian interpretation of probability. It enables us to quantify the uncertainty based on the evidence that we see. So in this example, the evidence was the satellite images. Okay, in the pattern recognition, that is important to us is an example of the Bayesian interpretation is that if you remember that we talked about the example of polynomial fitting. In that case, maybe you think that, okay, the random variables are the data, because we don't know the data, the true distribution of data, and data is coming from a distribution that we don't know about that, and so the random variables are the data. Okay, but in the Bayesian interpretation, it has a very different perspective. In the Bayesian interpretation, we are interested in the uncertainty of the model parameters, because at last we want to have the true model parameters, and so we want to know how much we are confident in the W's, in the model parameters, or how much there is uncertainty in the model parameters. So this is the we are talking about it. We are going to talk about it in a more clear way in some minutes later, but for now let me to show the data set with T1 to Tn. Okay, this is actually the example of polynomial fitting, and these t's are the target values. Okay, and we have n data points. The probability of the weights or model parameters given data with Bayes theorem is P of data given W times PW divided by P of D. And in the Bayesian interpretation, we call P of D given W the likelihood, because it tells us how much the probability of observed data is probable when we have certain setting of W, okay, so certain setting of model parameters, and we call this posterior, because when we see some data, we derive new W's. Okay, we change our intuition about the W based on the observed data. So we call it posterior, and we call the P of W prior, because before we see n data, we have some kind of prior about the P of W and the distribution of the parameters, and after observing the data, we change our mind about the W's. Okay, so we could say that the posterior is proportional to likelihood times prior. Okay, and don't worry too much about actually these, because this is actually just a normalization factor. As you know, we could expand this based on probability density function of dataset given W times P of W dW, and this is actually a number. When we divide this by this number, this is actually a normalization constant, which makes this integration equal to 1, because it should be a probability density function, so its integration should be 1, and this denominator just a number, just a normalizer number to makes this integration equal to 1. Okay, so in both Frequentist approach and the Bayesian approach, the P of dataset given W's is important. It is very important. Okay, but we have some fundamental difference between the Bayesian approach and Frequentist approach. As I mentioned, in Frequentist approach, we see the W as fixed parameters, and and we suppose that the dataset is random. The dataset is random variable. In contrast, in Bayesian approach, it says that okay, W's are random variables, but the dataset is not a random variable. And this is difference between the Bayesian approach and Frequentist approach. Now, what is the advantage of Bayesian approach? One advantage is that in Bayesian approach, if we look at this equation, we can see that we include the prior. The inclusion of prior sometimes help us. For example, let's say you toss a coin and you see that that coin in 3 times it has head. Now, if you want to estimate the probability of coin being head, if you want to calculate this with the frequentist approach, you should maximize the maximum likelihood of this event based on this. If you maximize this, you end up with your estimation is that equal to 1. It is pretty absurd because it says that your estimation of probability of coin being head is 1. So it tells you forever when you toss that coin you will see head, which is very unlikely. As opposed to this approach, if you use Bayesian approach, you should use this, and in this one you use the prior on the probability of being head. So in 3 times you will not get a very biased decision. So it is the advantage of Bayesian approach, and it is actually a very important difference between the frequentist and Bayesian approach. But it is very important to note that the Bayesian approach is sometimes performs very poorly when we do not know much about the prior, or our prior is not very good. So if we have poor prior, we will get bad results. And this is one reason is why we use the frequentist approach, which is cross-validation in later. The Bayesian approach is not always the best option for us, especially when we do not know much about the prior, or we do not have a strong intuition about the prior. So in that situation, maybe it is better to use the frequentist approach rather than Bayesian approach. As an important distribution, maybe it is better to introduce you with Gaussian distribution. Probably most of you know about that, but if you don't know, it is very very famous distribution. We tell that in the next sessions why it is so important, but for now you should actually think of that as a distribution, as a density function which has two parameters, and it is defined by this equation. And we call the mu, this parameter mu, mean, and sigma square variance, and we call the square root of sigma squared standard deviation. If you calculate the expected value of x, which is the integration of the probability density function times x dx, it is equal to mu. So this is one reason that we call this parameter mu mean, because it is the mean of this distribution. And if you calculate the x2, it is equal to mu squared plus sigma squared, so the variance of x, which is the expected value of x squared minus expected value of x squared, it will be sigma 2 or sigma squared. So this is the reason that we call this parameter variance, because it is the actual variance of the distribution. For the d-dimensional case, this is actually for just one dimensional. If we have some more than one dimension, we have mu as vector, because we have the x is a vector. It has some different random variables, so each of them has certain kind of mu parameter. So this is a vector, and this is the covariance matrix. So this is the matrix. We could write it as 2p d over 2 times the determinant of sigma power to 1 over 2 and times the exponential of 1 over 2x minus mu transpose sigma inverse and x minus mu. This is for d-dimensional case, which we saw an example at the first of session. You could see that this is called multivariate normal, because in this case we had some different random variables in a vector, and each of them has Gaussian distribution, and they could be correlated to each other with this matrix. So this is called multivariate Gaussian distribution. Okay. It is good to see an example of how to estimate the parameters of this distribution. Let's say you have some you see a sequence of n samples, and these samples are IID, independent identically distributed random variables. So if they are IID, and we know that this comes from this distribution, the Gaussian distribution. So if they are IID, means that they are independent. So we could convert this to the multiplication. We talked about it in the last session. For two or some independent random variables, we could convert this to a sum, to a multiplication of the probability density functions. Now, if we want to use the Frequentist approach, and so to estimate the parameters mu and sigma squared, we could use the maximum likelihood. So we want to maximize this with mu and sigma squared. In other words, we want to get mu and sigma 2 of maximum likelihood, which maximizes this multiplication. Maximizing this multiplication maybe is hard, so it is very common to get log from this equation, and in other words, maximize instead of maximizing the likelihood, maximizing the log likelihood of this. So because with taking the log from this equation, the maximum doesn't change, because the log is a monotone increasing function. So we will use the log of this, which is you could calculate it yourself if you want to make your calculus better. I don't know, it is very beneficial. Okay, anyway, so it is something like this, and if you want to, for example, obtain this mu, you just need to maximize this with regarding to mu. So the mu is, for maximizing this, you need to just put the derivative of this with respect to mu equal to 0. So in this case, you will obtain that your estimation from mu is the sample mean, because this is sample mean. So you see some examples and you want to estimate the mu or mean of the Gaussian distribution, you could just calculate the sample mean and estimate the mu from here. and also for sigma squared you will end up with this. Okay, now sometimes it is important to know that, okay, if we see our estimation as a random variable and we repeat the experiments so much times, we want to know that is our estimation is biased or unbiased. In other words, let's take the expected value of mu hat over the data set. In this case, we will end up, if you calculate this, we could derive this is equal to mu. So it is the real mu parameter, mean parameter of the Gaussian distribution. But if we calculate the expected value of sigma squared, estimated sigma squared with maximum likelihood, in this case you will end up with this. So in this case you could see that the maximum likelihood estimation underestimate the real parameter. So maybe you see that in some textbooks we have some unbiased version in the statistics for the estimation of variance, for the unbiased estimation of variance. In this case we define it in this way to have this. Now if we define our estimation in this way, this could be an unbiased estimation of the variance. About the advantages and disadvantages of maximum likelihood, we will talk about it in much more detail later, so don't worry too much about it. This is just an introduction about that. So I think this is enough for this session. I hope that you are getting familiar with the Bayesian probability, the Bayesian perspective, the Frequentist perspective, the Gaussian distribution, and maximum likelihood. Just getting the idea is enough for now, and you could write the codes that I showed you yourself. It is very good to practice it yourselves. And yeah, that's it for this session. Hope to see you. Bye.